Hello everyone, so today's question is called smallest subtree of all deepest nodes. Given a subtree, given a binary tree, the depth of each node is shortest distance to the root. Return smallest subtree such that it contains all deepest nodes in original array. So for example, this is my question. Let's just take this one. So for example, this is the binary tree we have, and we need to find this smallest deepest subtrees. What was the question, right? Smallest subtree with deepest nodes. So you can see over here what we can think is like, so basically like this node has depth equals to 0, right? These two nodes have depth equals to 1. These four nodes have depth equals to 2. These two nodes have depth equals to 3. Now you can see that the deepest nodes is basically these two, right? Because they have depth equals to 3. Okay, and we need to return their basically parent, so we'll simply return this, because this tree will be forming a subtree. Okay, we can make it more clear. So let's just add one more node over, say, here. So let's say we have a node over here. Now what will happen is, again we will check. This is basically like, okay, so God. So basically I'm trying to say that we have another node over here. Okay, and again its depth is 3. So this one has depth equals to 0. These two depth equals to 1. These four depth is 2. Now these three has depth 3. Okay, now our answer won't be this, but we'll check what is the common parent for the leftmost and rightmost, right? So for leftmost and rightmost, the common parent is what? This node, right? So we'll need to return this one, this root node. Okay, so this was the basic idea of the question. Now this question can be solved in two ways. The first one is where you have to find depth of each subtree. Okay, so over here we were finding depth of each node, but in the question we'll find depth of each subtree. Now what is depth of each subtree? Okay, so what will be the depth of this complete tree? It will be 1, 2 and 3, right? Because it's the longest. Yeah, so it will be 3 for this subtree. Now we'll find depth of its left subtree and right subtree. For this you can clearly see that the left subtree has more depth, right? This subtree has more depth, so we will move over here. Now we'll do it's the same thing. Now for 5 we'll check the depth of its left subtree and the depth of its right subtree. Over here the depth of right subtree, which is 274, is more than its left subtree. So now we'll make a pointer point to this, that is 2. Now again we'll check depth of its left subtree and its right subtree, right? Again now we'll see that the depth of both the subtrees are same, which is 0, right? So we'll return the value 2. So that was the basic idea. I hope it was clear. I'll explain it again through the code. So we have to find depth of each subtree. Now if depth of left subtree is more than depth of right subtree, that was in this case the depth of left subtree was more than right subtree, so we moved to left subtree and we did the same process again, right? So we'll say move to left subtree and check again. Now if depth of left subtree is less than depth of right subtree, we'll move to right subtree and do the same thing again. And whenever we get both the subtree have same depth, we'll simply return the root value, because then that will be the start of deepest subtree. Okay, so now the code section. So the first thing is you need to understand this code, which is basically it is finding depth of each subtree. So this is finding basically the depth of each subtree. Now it says that if whenever we have node equals to null, that is the basic condition. Now once done with that, we'll say return 1 plus max of depth of left or right. Okay, it's recursion again. So for example, if we have this tree and this tree, it's very messy, but I hope you understand. So this tree and this tree, so I'll say return for this 3, I'll say return 1 plus depth of this or this, whatever is the maximum. So since this is maximum, it will return what? 1 and 2. So it will return 2 plus 1. Okay, so this is the code for finding the depth of each subtree. Now this code says that again, if root is null, then we'll return null. Now we'll find left subtree's depth with this statement, and we'll find right subtree's depth with this statement. Now if they are same, we'll simply return root. If they are not same, and if one of them is big, let's say if left subtree's depth is bigger, then we'll do the same thing again, which is we'll use recursion and we'll call the function again for the left subtree's root, or else we'll do it for the right. Okay, now second solution. So if you see over here, we have to again and again find depth of the subtrees, and that can take so much of space and time because we are finding depth of each subtree again and again. So what else we can do is we can use another method where we'll find LCA using breadth first search. Now I'll explain it again. So the second method, if you think about it, we are trying to find the deepest nodes and then we are returning its lowest common ancestor. So what is lowest common ancestor? For example, if I take this node and I take this node, for these two nodes, the lowest common ancestor will be this node, right? For example, another, if I take, let's say, this node and this node, then the lowest common ancestor, that is the lowest node with what they are related, is this node, right? I mean, for this and this, the lowest common ancestor will be this. Now our answer, so this is the lowest two nodes, right? So if we see the lowest common ancestor of this or this and this is this, and that is our answer. We'll see another example. So over here, for 7 and 4, what is the lowest common ancestor? 2, right? And that is our answer. We'll take one more example explaining about lowest common ancestor. If I take 6 and let's say I take 6 and 0. Okay, so for 6 and 0, what is the lowest common ancestor? Is it 5? No, 5 is related with 6, but 5 is not related with 0. Is it 1? No, because 1 is not related with 6, but it is related with 0. Is it 3? Yes, because 3 is related with 6 and it is also related with 0. So answer will be 3. Okay, so we have understood what is the lowest common ancestor, and we have understood that we need to find lowest common ancestor for the last last, that is this, like the lowest nodes, lowest common ancestor, and we'll get the answer. So how will we do that is, so basically what we'll do is we'll use breadth for search for finding the last two nodes, right? Last two nodes, which is for example over here the last two nodes is 7 and 4. So first thing we need to find the last two nodes. How will we find is we'll go breadth wise. So we'll go with 3 and then we'll go with 5 and 1, and then we'll see, okay, they have child again. For example, like I'll start again. So I'll see 3. Now I'll say, okay, 3 has child again. So I'll go to the next level and I'll say, okay, 5 and 1. Now 5 and 1 again they have child, so I'll go, okay, fine. Now 5 and 1 have these many children, and now 6 and 2, I'll see, okay, 6 has no child, 2 has 2 child, 0 has no child, 8 has no child. So now the last depth will be this. Okay, so I found the lowest nodes. Okay, so how can we find it is using depth for search method. We'll find the lowest nodes and we'll simply return the lowest common ancestor. Now the code for this, so if root is not there, or root's left or right is not there, we'll simply return root. So if root is not there, the answer will be null. If root's left is not there, then it will be root, and yeah, if right is also not there, it will be root. Okay, now how we'll do breadth for search is we'll use a queue and we'll keep adding the child node as I was going over here. So we'll first go with 3. Now we'll add its child node, that is 5 and 1, in the queue. Okay, now again I'll go to 5 and I'll add its child nodes, that is 6 and 2, in the queue, and then I'll go to 1 and I'll add one's child nodes in the queue, that is 0 and 8. Okay, and similarly we'll continue the process, and if you see whenever my queue will start with 0 or end with the last element, I'll explain. So I'm pushing the first root node in the queue, so it's pushed. Now the queue has 3, right? Now while queue is not empty, level size is equal to queue size. So queue size right now is 1. Okay, so level equals to 0, level, so it's basically like it's moving, traversing the entire queue. Now tree node queue front, so it's saying that take the queue front, which is 3. So now node value is 3. Okay, node is equal to 3. Now queue.pop, so queue had 3 and we are popping it. Now if level is 0, yes, then leftmost node will be this 3. So leftmost node is right now 3. And is level equals to level size minus 1? Yes, it is, because level is 0 and level size was 1. So 1 minus 1 is 0. So rightmost is also 3. Now we'll check if node left is there. So yes, node left is 5 and node right is 1. So we'll push both of them in the queue. So now my queue will be looking like it will have 5 and 1, right? 5 and 1. Now it will check again for 5 and 1 and it will go to 5 and see. It will pop the 5 and now size is 2. So it will pop the 5 and see if it's 0. Yes, it is 0. So now node will be 5. Leftmost node will be 5. Now if level is equal to level size minus 1, no, it's not the endmost, so it will remain 3 right now. And if node left is there or node right is there, basically yes, it is 6 and 2. It will push 6 and 2 in the queue. So it will continue doing it, and finally we'll get the leftmost and rightmost. For example, if in this we got 3 as leftmost and rightmost, when we traverse this level we'll get 5 and 1. In this level we'll get 6 and 8 as leftmost and rightmost child, and then in this case we'll get 7 and 4 as rightmost and leftmost child. Now all we need to do is pass a function saying that take the root node and take the leftmost and rightmost and find the lowest common ancestor of it.